Look up at the night sky on a clear evening, and what do you see? Stars, planets, the silent dance of celestial bodies. But there's something else up there, something we've left behind. A hidden ocean of human-made objects, forgotten and adrift, broken satellites, abandoned rocket stages, even a lost glove or two, all traveling at unimaginable speeds in the endless dark. Right now, more than 128 million pieces of space debris orbit our planet, a chaotic and growing constellation of our own making. For decades, we've treated Earth's orbit as a junkyard, a place to discard what we no longer need after reaching for the stars. But what if we've been looking at this problem all wrong? What if this so-called trash is actually a treasure, a vast, untapped resource waiting to be unlocked? Imagine a future where the very debris we once feared becomes the foundation for a new era of innovation. A future where discarded satellites are transformed into orbital power stations, where fragments of old rockets are forged into radiation shields for Mars-bound astronauts, and where the clutter of our past ambitions fuels the next great leap in exploration. This isn't science fiction, it's the exciting and urgent frontier of sustainable technology, and it's happening right now. In this video, we'll explore 24 revolutionary ideas born from space junk technologies that could reinvent life on Earth and beyond. These innovations blur the line between waste and wonder, turning environmental challenges into extraordinary opportunities. This journey is about more than just cleaning up our cosmic backyard. It's about rethinking what's possible when creativity meets necessity. It's about harnessing the materials we've already sent into space to build a brighter, more sustainable future, one where humanity's footprint in the cosmos becomes a cycle of renewal rather than waste. From converting debris into advanced materials to powering cities with recycled solar arrays, the solutions we'll uncover are as inspiring as they are ingenious. So join us as we dive into the stories, the science, and the brilliant minds turning danger into discovery, and discover how the junk orbiting above us might just hold the key to tomorrow's world. Look up, and you're not just seeing stars, you're looking at a floating junkyard. Since the launch of Sputnik 1 in 1957, every satellite deployment, every crewed mission, and every rocket launch has left a mark. Not in the history books alone, but in the physical space around our planet. Imagine a realm where a single lost wrench or a flake of paint travels at 17,500 miles per hour, 10 times faster than a bullet. That's the reality of low Earth orbit today. It's a chaotic sea of fragments, defunct satellites the size of school buses, discarded rocket upper stages, lens caps, nuts, bolts, and even the occasional tool dropped by an astronaut. This isn't just clutter, it's an escalating environmental crisis. A single collision between two objects can generate thousands of new fragments, each one a potential projectile capable of crippling a functioning satellite or threatening the International Space Station. This cascade effect, known as the Kessler syndrome, paints a worrying picture of an orbit so congested that certain altitudes become unusable. But within this immense challenge lies a profound opportunity. The very materials that pose such a danger are fundamentally resources. They just happen to be in the wrong place. Consider the composition. Over 9,000 metric tons of material are currently orbiting Earth. A significant portion of that is high-grade aerospace aluminum, titanium alloys, and other valuable metals, all launched at immense cost and energy. For decades, the mindset was one of disposal. We used orbit as a dumpster. Now, a new concept is taking hold: orbital sustainability. This isn't just about cleaning up, It's about creating a circular economy in space. Instead of seeing a derelict satellite as waste, visionaries at agencies like NASA and the European Space Agency are starting to see a salvage yard. They're investing in mission concepts focused not on avoidance, but on active debris removal and repurposing. The European Space Agency's Clear Space mission, for example, aims to capture a piece of debris and safely deorbit it, demonstrating the technology needed for cleanup. But the next logical step is to ask, why just throw it away again? Why not break it down and use it? This shift in perspective turns a liability into an incredible asset. The necessity of dealing with this debris is now the mother of invention, driving some of the most creative engineering projects of our time. We're moving from a linear model of launch, use, discard to a circular one of launch, use, reuse, and remake. That 9,000 tons of metal isn't just trash, it's a pre-launched supply depot, a reservoir of raw materials waiting to be tapped. It represents a chance to drastically reduce the cost and environmental impact of future space exploration. Instead of launching every gram of material from Earth's deep gravity well, we can learn to live off the land, or in this case, off the orbital debris. This foundational idea that our greatest problem in space could become its most valuable resource is the bedrock upon which a new wave of technology is being built. It begins with a revolutionary way to approach construction, turning the junk of yesterday into the building blocks of tomorrow. Now, picture a swarm of sophisticated robotic craft, not just collecting this debris, but feeding it into their own bodies, transforming yesterday's satellites into tomorrow's tools. This is the promise of orbital three-dimensional printing using recycled metals, a concept that fundamentally changes how we approach construction beyond our atmosphere. The core idea is breathtakingly simple yet revolutionary. Why launch expensive, heavy new materials from Earth when we've already unintentionally placed thousands of tons of high-grade metal into orbit? These autonomous printers would act as orbital factories, capturing defunct satellites and spent rocket stages, then using furnaces and lasers to melt down the aluminum, titanium, and other alloys. This molten metal becomes the raw feedstock for their printers, meticulously building new structures layer by layer in the vacuum of space. The implications for cost and environmental savings are staggering. Launching anything into orbit is incredibly expensive, with current costs averaging around $1,500 per pound of material. A single large structure, like a new module for a space station, could require launching many tons of metal, a process that is not only costly but also consumes vast amounts of fuel and resources. By using what's already there, we bypass this entire inefficient system. This approach also makes space missions far more resilient. Imagine a critical component on a satellite fails. Instead of writing off the entire multi-million-dollar asset, a servicing craft could arrive, harvest material from a nearby piece of debris, and print a brand new replacement part on the spot. This is on-demand manufacturing at a cosmic scale, turning every mission into a potential repair shop and every piece of junk into a spare parts depot. This isn't just theoretical. Companies are actively turning this vision into reality. A pioneer in this field, Made in Space, developed the Archinaut project, a system designed to demonstrate large-scale additive manufacturing and assembly in the vacuum of space. Their vision involves robotic arms working in concert with 3D printers to construct massive structures, like enormous solar arrays or communication antennas, that would be impossible to launch in one piece from Earth. The process begins with collection. Specialized robots equipped with grappling arms and cutting tools would secure a derelict satellite. They would then carefully disassemble it, sorting the materials by type and composition. Metals are fed into a chamber where they are heated until molten, then extruded through a print head that follows a digital blueprint, building everything from simple brackets to complex, truss-like frameworks for new habitats or spacecraft. The potential end products are as varied as our ambitions in space. We could see the construction of entire new space stations, built from the skeletons of their predecessors, orbiting fuel depots for deep space missions, or even large-scale telescopes with mirrors printed to perfection in microgravity. This technology embodies a powerful new philosophy for our future in space, one of resourcefulness and sustainability, where nothing is truly wasted. The end of one mission's life becomes the literal foundation for the next, creating a continuous cycle of renewal high above our planet. It's a profound reminder that with a shift in perspective, what we see as an obstacle can be transformed into our greatest advantage. Now consider the most dangerous and invisible threat facing those future explorers: radiation. Beyond the protective bubble of Earth's magnetic field, astronauts are bombarded by a constant stream of cosmic rays and solar particles, an invisible hail that can shred DNA and dramatically increase cancer risk. Shielding against this is one of the single biggest hurdles for long-term missions to the Moon or Mars. But what if the solution to this existential danger is already floating around us, disguised as trash? This is the brilliant premise behind using space debris itself as radiation shielding. Imagine the hull of a lunar habitat, its walls not made from pristine materials launched from Earth, but from a dense composite armor of compressed satellite parts and discarded rocket fragments. Every piece of debris collected and processed adds another layer of life-saving protection for the crew inside, transforming a hazard into a guardian. The science behind this is both elegant and practical. Not all materials are equally effective at blocking high-energy radiation. Lead, for instance, is counterproductive as it can actually produce secondary radiation when struck by cosmic rays. The most effective shielding materials are those with low atomic numbers, packed with lightweight atoms like hydrogen. These atoms are excellent at absorbing and dispersing radiation energy without creating dangerous byproducts. It turns out that many components of space debris are rich in these very elements. The Kevlar and other composite materials used in satellite construction, the insulation foams, and even the leftover residues of rocket fuel all contain high concentrations of hydrogen. By compacting this mixed waste into dense panels, we can create a highly effective multi-layered radiation barrier. Research institutions are already proving this concept. Teams at places like MIT and NASA, our own research divisions, are experimenting with techniques to process and repurpose orbital waste into functional shielding. The process might involve robotic systems that can sort, shred, and then fuse debris together using heat or mechanical pressure, creating standardized blocks or tiles. These panels could then be used to line the outer walls of a habitat or even form a protective storm shelter within a spacecraft where crews could retreat during periods of intense solar activity. The key advantage is mass. Transporting enough dedicated shielding material from Earth to protect a Mars-bound crew would be prohibitively heavy and expensive. But by using what is essentially already there, we solve the mass problem while simultaneously addressing the debris problem. It's the ultimate 2-for-1 solution. Every kilogram of junk removed from orbit is a kilogram of radiation protection we don't have to launch. This approach moves the conversation about space debris far beyond mere sustainability. It becomes a matter of pure survival. For astronauts spending months traveling to Mars or years on a lunar base, this recycled shielding could be the difference between a healthy return home and a mission cut short by medical emergency. It embodies a profound shift in how we view our environment, whether on Earth or in space. Nothing is merely waste. everything is a potential resource waiting for the right application. The same piece of a derelict satellite that once threatened operational spacecraft could one day be the very thing that protects a human life millions of miles from home, turning a symbol of our past carelessness into a cornerstone of our future resilience. But what if we could take that same principle of repurposing and apply it to one of humanity's greatest challenges down here on Earth, the relentless demand for clean, reliable energy? The concept is nothing short of breathtaking. Imagine those very same skeletons of defunct satellites, once symbols of our orbital clutter, being transformed into the backbone of massive power stations in the sky. These wouldn't be ordinary solar farms, they would be orbital assets, soaking up sunlight 24 hours a day without the interference of clouds, night, or atmosphere. The sunlight in space is significantly more intense and consistent than anything we can capture on the planet's surface. By retrofitting the sturdy, existing frameworks of old communication satellites and rocket bodies with new, ultra-efficient solar cells, we could construct sprawling arrays that dwarf anything possible on Earth. This approach sidesteps the single biggest hurdle of space-based solar power: the astronomical cost of launching all that mass from the ground. Instead, we're using structure and material that's already paid its way into orbit, turning a cost center into a profit center. The process for building these orbital power plants is a masterclass in robotic efficiency. Specialized servicing spacecraft would be dispatched to carefully grapple with retired satellites that have reached the end of their operational life. Using advanced tools, these robots would methodically dismantle the old hardware, stripping away outdated communication payloads and electronics while preserving the valuable primary structure, the strong, lightweight trusses and booms that were originally engineered to withstand the brutal launch forces and the harsh space environment. These salvaged frameworks become the perfect foundation. Next, rolls of advanced, lightweight solar film or panels, launched from Earth in a compact form, would be robotically unfurled and integrated onto the old structure. The result is a new, functional power satellite assembled from the bones of the old, its total launch mass a fraction of what building from scratch would require. This vision is actively being pursued by brilliant minds at institutions like the California Institute of Technology. Their Space Solar Power Project is a landmark initiative developing the core technologies needed to make this a reality. They've successfully demonstrated prototypes of ultralight, deployable structures and integrated photovoltaics designed for this exact purpose. The final piece of the puzzle is beaming the energy home. This would likely be achieved through microwave or laser transmission, sending the power in a safe, focused beam to receiving stations on Earth called rectannas, which would convert it into electricity for the grid. The potential is staggering. A single large-scale solar power satellite could provide a constant baseload of gigawatts of clean power, day and night, rain or shine, to any point on the globe. It's a powerful dual solution, actively cleaning up the hazardous environment in Earth orbit while simultaneously generating a virtually limitless supply of clean energy to combat climate change below. We are quite literally turning the pollution of our past space endeavors into a sustainable power source for our future. This incredible synergy of cleanup and energy production perfectly illustrates how solving one problem can provide the key to unlocking another, leading us to look at the junk around our planet not as waste, but as a reservoir of invaluable resources. While we often picture space debris as inert hunks of metal, a significant portion of it holds a hidden, liquid treasure. Picture a specialized robotic probe, its design more akin to a deep space chemist than a simple garbage collector, gently docking with a spent upper stage rocket body that has been drifting silently for years. Its target isn't the rocket structure, but the toxic, sloshing residues of hydrazine or other fuel blends left trapped in its tanks. This is the frontier of water extraction from rocket fuel residues, a technology that treats every abandoned stage not as waste, but as a potential orbital oasis. Water is arguably the most valuable substance in space exploration. It's not just for drinking. Through electrolysis, it can be split into breathable oxygen for astronauts and hydrogen for rocket fuel. It's the fundamental building block for sustaining life and enabling travel. The cost of launching water from Earth is astronomical, currently sitting at tens of thousands of dollars per liter. Every single droplet that can be salvaged in orbit represents a massive saving in cost, weight, and risk for future missions, making the dream of sustained deep space exploration far more attainable. The concept builds directly on the incredible work already being done aboard the International Space Station. The ISS's environmental control and life support system is a marvel of recycling, capable of reclaiming over 90% of the water on board. It captures humidity from the air, condenses it, and even purifies astronaut urine, creating a nearly closed-loop system. This technology proves that in situ resource utilization is not just a theory but a working practice. The next logical step is to extend that principle beyond the station's walls and into the orbital environment itself, applying it to the resources we've unintentionally left behind. The process for extracting water from these derelict fuel tanks is a feat of advanced chemical engineering. After a probe securely attaches to a target rocket stage, it would deploy a system of specialized lines and pumps to carefully transfer the residual propellants. These leftover fuels are then fed into a compact but powerful chemical reactor. Inside this reactor, through carefully controlled processes like catalytic cracking or hydrolysis, the complex molecules of fuels like hydrazine are broken down. The goal is to isolate the hydrogen and oxygen atoms and recombine them into pure, potable water. Advanced filters would remove any contaminants or leftover toxins, ensuring the final product is safe for human use or for conversion into propellant. The other byproducts of this reaction, such as nitrogen, could also be captured and stored for use in habitat pressurization or as inert gas buffers. This transforms a dormant and frankly hazardous piece of space junk into a functioning resource depot. A single spent upper stage, which might have contained many tons of propellant, could still hold several kilograms of recoverable residues. A fleet of these extraction probes could effectively create a network of orbital gas stations, allowing future missions to refuel their tanks and top off their life support supplies without ever having to return to Earth. This approach offers a brilliant twofold victory for space sustainability. First, it actively mitigates a serious danger. Many of these abandoned rocket stages still contain unstable, toxic chemicals that could potentially explode, creating new clouds of hazardous debris. By safely removing and processing these residues, we neutralize that threat. Second, and more importantly, it establishes a practical, economical supply chain for the most critical resources in space, using materials that have already been paid for and launched. It embodies the ultimate ethos of a circular economy, where nothing is considered waste and everything has a purpose waiting to be discovered. This incredible resourcefulness, pulling the very essence of life from what was once considered poisonous refuse, sets the stage for an even more direct form of reuse, not just breaking down materials, but giving old technology a brand new mission. Think about the incredible instruments we send into space: high-resolution cameras that can spot a car from hundreds of miles away, sensitive spectrometers that can analyze the chemical makeup of a distant asteroid, powerful transmitters that can send data across the solar system. These are marvels of engineering, often costing hundreds of millions of dollars to design and build. And when the satellite they're attached to runs out of fuel or has a systems failure, we've traditionally considered the entire thing, including these perfectly functional instruments, to be lost. It's like junking a brand new, top-of-the-line camera just because the tripod broke. But a new, far more logical approach is emerging, the cosmic equivalent of an organ donor program for satellites. Instead of writing off these incredible machines, we can now envision a future where their still beating technological hearts are given a second life on a brand new mission to the depths of space. The economics behind this idea are utterly compelling. Developing and qualifying a new scientific instrument for the harsh environment of space is a long, arduous, and fantastically expensive process. It can take a decade and cost billions. Yet, when a communications satellite in geostationary orbit is retired, it often has a suite of components that are still in perfect working order. Its guidance systems, its star trackers, its reaction wheels, and its communication antennas have years, even decades of life left in them. The satellite's mission ended not because its eyes and ears failed, but because it simply ran out of the fuel needed to stay in its correct position. Companies like Astroscale are already pioneering the technology for this very purpose, developing autonomous servicer spacecraft designed to safely rendezvous with these retired assets. Their initial goal might be to deorbit them, but the next logical step is not just removal but harvesting. The process would be a delicate ballet of precision robotics. An autonomous servicer craft would carefully approach a derelict satellite, using a suite of sensors to map its structure and identify specific components marked for recovery. Using specialized robotic arms equipped with custom tools, it would then methodically detach these valuable instruments, unbolting a communication dish, unplugging and carefully extracting a sensor package, or even retrieving an entire onboard computer. These components would be stored in a protected cargo bay. Before being integrated into a new spacecraft, each one would undergo a rigorous series of diagnostic tests in a specialized orbital facility to verify its integrity and performance after years of exposure to the vacuum and temperature swings of space. Once certified, these upcycled parts become the core of a new, mission-specific probe. Imagine a small, low-cost spacecraft assembled from this salvaged hardware, its brain a computer from an old weather satellite, its voice a transmitter from a defunct TV broadcast satellite, and its eyes a camera from a retired Earth imaging mission. This Frankensatellite, born from the best of the old, could be sent on a one-way trip to explore a near-Earth asteroid, to swing past Jupiter, or to become a dedicated monitor for solar weather, providing early warning for events that could threaten Earth's power grids. The savings are monumental, slashing both the development time and the cost of deep space missions by orders of magnitude. This approach does more than just clear orbital clutter. It fundamentally accelerates our pace of exploration by leveraging the incredible investments we've already made. It embodies a timeless principle of efficiency, waste not, want not, and this philosophy of finding value in every single piece of material leads us to an even more fundamental application, using the most dangerous fragments of debris not for their technology, but for their raw, physical bulk as a form of protection. Moving from the grand vision of repurposing entire satellites, we now turn to a more granular yet equally ingenious application, transforming the most numerous and dangerous form of space junk into a life-saving barrier. Envision the hull of a next-generation spacecraft or a lunar habitat, its outermost skin not a smooth, pristine shell, but a textured, composite armor crafted from the compressed fragments of our orbital past. This isn't just a patchwork solution. It's a highly engineered shield designed to withstand the relentless hailstorm of micrometeoroids and other debris that travel at speeds exceeding 22,000 miles per hour. At those velocities, even a fleck of paint can punch a crater into solid metal, posing a catastrophic risk to any structure or crew. The brilliance of this technology lies in its elegant reversal of fortune. The very particles that constitute the impact threat are themselves harvested and reconfigured into the primary defense against it. The core principle behind this kind of shielding is energy dissipation. It's not about creating an impenetrable wall, but rather designing a smart, sacrificial buffer that absorbs and disperses the immense kinetic energy of a hypervelocity impact. The most effective design, proven over decades of research, is the Whipple shield, a concept involving multiple spaced layers. The outer layer, often a thin sheet, is designed to shatter the incoming projectile upon impact, turning a single, dangerous bullet into a cloud of less energetic fragments and vapor. This expanding cloud then spreads out and hits a second, thicker layer, which has the mass and strength to absorb the remaining energy without being breached. By fabricating these outer sacrificial layers from the compressed remnants of old satellites, rocket fairings, and other debris, we create a shield that is both highly effective and incredibly resourceful. The manufacturing process is a fascinating blend of orbital recycling and advanced materials science. Autonomous collector craft would be tasked with gathering the countless small fragments that populate low Earth orbit, using nets, foam, or other innovative capture systems to safely secure these high-speed projectiles. Once collected, this melange of aluminum, titanium, ceramics, and composite materials would be sorted not just by composition, but also by size and shape. This sorted debris would then be fed into a processing unit where it could be heated, compressed, and fused together using techniques like spark plasma sintering or microwave bonding. The result is a new, engineered material, a flexible, tile-like panel with a heterogeneous structure that is uniquely suited to disrupting impacts. These panels could then be robotically attached to the exterior of spacecraft, space stations, or planetary habitats, creating a customizable and upgradable protective skin. Studies conducted by agencies like the European Space Agency and NASA Orbital Debris Program Office have consistently shown that such multilayer shields, even when made from recycled components, can perform on par with, or even exceed, the capabilities of shields built from virgin materials launched from Earth. The inherent variety in the recycled material, the mix of densities, melting points, and material properties, can actually create a more complex and effective energy-absorbing structure than a uniform sheet of metal. This approach offers a monumental advantage in mass savings. Launching heavy, dedicated shielding from Earth's surface is one of the most mass-prohibitive aspects of space exploration. By manufacturing protection in situ from materials that are already in orbit, we bypass this colossal expense and logistical nightmare entirely. This technology represents a profound philosophical shift in how we approach both danger and resources in the space environment. It moves us from a mindset of passive vulnerability to active resilience. Every piece of hazardous debris successfully collected and converted into a shield panel directly reduces the overall threat level in orbit while simultaneously increasing the safety of our assets. It's a continuous cycle of improvement. The more debris Chinese letter, the safer space becomes, and the more material we have to make our vessels and habitats even safer. This elegant solution demonstrates that in the challenging environment of space, there is no such thing as true waste, only materials waiting for the right application, where a former menace can become a guardian. While we often focus on the purely practical benefits of recycling space debris, some of the most inspiring applications merge utility with sheer wonder. Imagine a warm summer evening, a crowd gathered on a beach or in an open field, their faces turned upward not to watch a random natural event, but a scheduled celestial performance. High above, a small capsule releases a carefully curated collection of space debris, tiny paint flakes, fragments of aluminum, and other non-hazardous materials. As these particles hit the upper atmosphere, they don't simply vanish, they ignite, streaking across the sky in a brilliant, multicolored display of human-made meteors. This is the concept behind artificial meteor showers, a technology that transforms the abstract problem of orbital clutter into a tangible, beautiful experience for everyone on the ground. The potential uses for such a spectacle are as vast as the sky itself. Major cities could bid to host these events, driving tourism and creating a new form of cosmic entertainment, like fireworks on a planetary scale. Imagine a New Year's Eve celebration in Sydney or a national holiday in Washington, D.C., capped off with a custom-designed light show authored from the edge of space. Beyond pure entertainment, the educational value is immense. Each event could be paired with information campaigns, museum exhibits, and live broadcasts explaining the origin of the light show, that each streak of light represents a piece of pollution removed from orbit, a hazard turned into harmony. This transforms public perception, making the critical issue of space sustainability visible, engaging, and personally meaningful. It fosters a powerful connection between life on Earth and the environment we've created just beyond our atmosphere, turning apathy into advocacy through awe. Creating this safely and reliably requires a fascinating blend of precision engineering and orbital mechanics. The process would begin with dedicated collector craft designed to target the smallest and most benign class of debris. Using gentle methods like foam-based capture or fine nets, these robots would gather kilograms of material like old thermal coating particles, tiny screws, and slag from past engine firings. This material would then be processed and packaged into a specialized delivery capsule, often referred to as a pearl pod, for its ability to carry and release its valuable contents at the perfect moment. The true magic lies in the guidance and release technology. The pod itself would be equipped with a small guidance system and thrusters, allowing it to maneuver into a highly precise re-entry trajectory. It wouldn't just be thrown overboard, it would be placed on a specific path with the accuracy of a master archer firing an arrow. The release would be timed and targeted to occur over a specific, pre-approved patch of ocean or uninhabited territory, ensuring total safety. The altitude, angle, and velocity of the release are all meticulously calculated to guarantee that every particle burns up completely in the mesosphere, far above any aircraft, creating the optimal visual effect without any risk to people or property on the ground. By varying the composition of the debris in each pod, mixing different metals and materials, companies could even engineer the color of the meteors, creating showers of brilliant blues, vibrant greens, or deep reds for a truly customized experience. This ambitious vision is already moving beyond science fiction. Japanese company ALE has been developing related technology for years, aiming to create artificial meteor events using specially manufactured particles. The leap to using actual space debris is the next logical and profoundly poetic step in this evolution. This application stands as a powerful testament to a broader philosophy that solving our greatest challenges doesn't have to be a grim, purely technical endeavor. It can be beautiful, inspirational, and deeply human. By turning space junk into a source of public joy and education, we reframe the entire narrative of our relationship with the orbital environment. It's no longer a distant problem for rocket scientists to worry about. It becomes a shared resource for creating moments of collective wonder. This creative approach demonstrates that the value of cleaning up our act in space isn't just measured in safer satellites or reduced costs, but also in its ability to reignite public passion for exploration and stewardship, reminding us that our future in the cosmos can be both sustainable and spectacular. Now, let's shift our focus from applications in space to a concept that bridges the heavens and Earth in the most direct way imaginable. We're talking about capturing valuable materials from orbit and bringing them back home to be used in our most advanced manufacturing sectors. This isn't about launching things into space anymore. It's about bringing a piece of space back to us. Think of the countless derelict satellites and spent rocket stages. They aren't just clutter, they're essentially pre-launched ore, rich with some of the most sought-after metals on the planet. We're looking at high-grade aerospace aluminum, incredibly strong titanium alloys, and even specialized superalloys that are notoriously difficult and expensive to produce terrestrially. The vision is to see companies develop sophisticated systems to harvest this orbital treasure, safely return it to Earth, and feed it directly into the production of high-performance products. Imagine the landing gear of a next-generation aircraft or a critical, load-bearing component for a medical implant being forged from titanium that once circled our planet as part of a communications satellite. The story of that metal, from a functioning machine to forgotten debris and back to a vital component in a new technology, creates a powerful narrative of a truly closed-loop economy. The allure isn't just in the novelty, it's in the potential for superior material properties. The microgravity environment of space offers a unique advantage for material formation that we simply cannot replicate in Earth's gravity. On our planet, the process of melting and solidifying metal is plagued by convection currents and sedimentation. Heavier elements sink, lighter elements rise, and impurities get trapped in the crystalline structure, creating weaknesses and inconsistencies. But in the quiet, weightless conditions of orbit, these forces vanish. Metals can be melted and resolidified with a level of uniformity and purity that is virtually impossible to achieve in any terrestrial foundry. This can result in alloys with fewer internal defects, more perfect crystalline structures, and subsequently enhanced strength, lighter weight, and greater resistance to fatigue and corrosion. A bracket made from aluminum refined in microgravity could be significantly stronger yet lighter than its Earth-made counterpart, a critical advantage in industries where every gram and every ounce of performance counts. Turning this vision into reality requires a meticulously choreographed orbital ballet. The process begins with a specialized servicer spacecraft, equipped with advanced sensors and robotic arms, rendezvousing with a pre-identified piece of large debris like a derelict rocket up a stage. The robot would first secure the object, then begin the precise work of cutting and dismantling it, separating valuable metal panels and structural components from other materials like composites or outdated electronics. These choice pieces of metallic debris would then be fed into a compact, orbiting processing facility. Inside, they might be melted down in an electromagnetic or solar furnace, allowing contaminants to separate out in the zero-G environment. The purified molten metal could then be cast into standardized ingots or other simple forms ideal for transport. The final and most daring step is the return journey. These precious ingots would be carefully loaded into specially designed, heat-shielded re-entry capsules, not unlike the capsules used to return scientific samples from the International Space Station. These capsules would be equipped with guidance systems to ensure they target a precise and safe recovery zone, like a vast, uninhabited desert or a designated area in the ocean. After surviving the fiery plunge through the atmosphere, they would deploy parachutes and be retrieved by a recovery team. Back on Earth, these space-forged metals would enter the supply chain for aerospace firms, medical device manufacturers, and high-tech automotive companies, eager to incorporate material with such a unique pedigree and superior properties into their most demanding products. This creates a tangible link between cleaning up our orbital environment and directly enhancing technological advancement on the ground, proving that the benefits of space sustainability are not confined to space alone. Now, let's push the boundaries of efficiency even further with a concept that feels like something straight out of science fiction: a spacecraft that literally consumes the problem it was sent to solve. Imagine a dedicated cleanup craft, but instead of a limited fuel supply dictating its mission lifespan, it's equipped with a unique kind of engine, one that grinds up the very debris it collects into a fine, metallic powder and uses that powder as its propellant. This is the revolutionary idea behind debris-powered propulsion systems, a technology that transforms the hunter into a true predator, sustaining itself on the clutter of orbit to fuel its endless hunger for more. It's the ultimate expression of a circular economy, not just reusing materials, but converting a direct threat into the very energy needed to eliminate it. The principle behind this is a brilliant twist on well-understood physics. Traditional rockets carry all their fuel and propellant with them from the launch pad, a deeply inefficient model because you have to burn fuel to carry the fuel you haven't burned yet. This new system shatters that paradigm. It operates on concepts similar to ablative propulsion or electromagnetic mass drivers. In one proposed method, captured debris, a mix of aluminum, titanium, and other metals, is fed into a grinding mechanism, pulverizing it into a consistent microscopic dust. This dust is then injected into a combustion chamber or an electromagnetic accelerator. When ignited by a laser or an electric arc, this metallic dust rapidly expands, creating a high-velocity plume of superheated gas and particles that shoots out of a nozzle, generating thrust according to Newton's third law. For every action, there is an equal and opposite reaction. In a more advanced mass driver concept, the powdered debris could be electromagnetically catapulted out at tremendous speed, providing a clean, efficient push without any combustion at all. This isn't merely a theoretical exercise sketched on a whiteboard. Researchers and engineers are actively developing the building blocks for this technology. Theoretical models developed at institutions like the University of Southampton and private aerospace firms have shown that the specific impulse, a measure of propulsion efficiency, of such a system could be competitive with other in-space propulsion methods, while offering the unparalleled advantage of indefinite operation. Small-scale laboratory tests have successfully demonstrated the feasibility of using metal powders as a viable propellant, proving that the energy density contained in these materials is more than sufficient for the task of maneuvering around Earth orbit. The challenges are significant, of course, involving the creation of robust machinery that can handle the unpredictable nature of space junk, from grinding different material types to preventing clogs in the feeding system. But the foundational science is sound and incredibly promising. The benefits of perfecting such a system are nothing short of transformative for orbital sustainability. A single servicer craft equipped with a debris-powered engine could operate for years, perhaps even decades, without ever needing a refueling mission from Earth. It would be the ultimate self-sustaining cleaner. After deorbiting a large, defunct satellite, it wouldn't need to return to a depot. It could simply harvest a small portion of that debris, process it into fuel, and use that new energy to propel itself to its next target. This creates a powerful positive feedback loop. The more debris it removes, the more fuel it has available to remove even more debris, allowing it to clear vast swaths of orbit in a single, extended mission. The cost savings would be astronomical, eliminating the single greatest operational constraint for these missions: This approach moves us from a model of periodic, expensive cleanup campaigns to one of continuous, autonomous stewardship, where the problem of space junk actively contributes to its own solution. This incredible vision of a self-perpetuating cleanup machine forces us to expand our thinking, to consider how this principle of using waste for sustenance could be scaled up to support not just spacecraft, but the humans living inside them. But the challenge of long-term life support in space goes far beyond just managing metal and machinery. It's about sustaining the most fragile element of any mission, the human crew. For every astronaut on a space station, the most critical resources are the ones we often take for granted on Earth: clean air to breathe, fresh water to drink, and nutritious food to eat. Currently, these essentials are regularly shipped up from our planet at immense cost, a logistical chain that is simply unsustainable for future missions to Mars or beyond. But what if the very waste produced by the crew could be transformed into the resources needed to keep them alive? This is the incredible promise of organic waste converters, a technology that closes the loop on life support by turning yesterday's trash into tomorrow's breakfast. This concept is already being proven every single day aboard the International Space Station. The Environmental Control and Life Support System, or ECLSS, is a marvel of engineering that recycles about 90% of the water on board. It captures humidity from the crew's breath and sweat, and even purifies urine, turning it back into clean, drinkable water. But the next frontier is tackling solid waste: food scraps, packaging, and human waste. The vision is to take this organic refuse and feed it into advanced, compact bioreactors. Inside these sealed units, a carefully curated community of microbes feasts on the waste, breaking it down through processes like anaerobic digestion. The output isn't just disposal, it's production. The process yields two incredibly valuable products: a nutrient-rich slurry that acts as a powerful fertilizer, and biogas, a mixture of methane and carbon dioxide that can be used for energy or even broken down further into its core elements. Now, imagine supercharging this system for a future deep space habitat. The innovation lies in tailoring specific strains of bacteria or fungi to handle not just natural organic waste, but the synthetic materials that are ubiquitous in space debris. Think about all the plasticized food packaging, the composite materials, and the various polymers that make up a significant portion of a station's disposable items. By developing specialized microbes that can digest these synthetics, we could effectively process almost everything a crew discards. The procedure would be a continuous cycle. Waste is collected from throughout the habitat, sterilized to eliminate any potential pathogens, and then fed into the bioreactor tanks. The engineered microbes go to work, and the resulting liquid fertilizer is pumped directly into hydroponic or aeroponic gardens, where it nourishes crops of lettuce, tomatoes, and other fresh vegetables. These gardens do more than just provide food. They are also natural air revitalization systems, absorbing carbon dioxide and producing fresh oxygen through photosynthesis. This creates a beautiful, self-sustaining loop where nothing is truly wasted. The crew eats food grown from the garden, produces organic waste, and that waste is converted back into the fertilizer that grows more food. Simultaneously, the system contributes to a constant supply of breathable air. This dramatically reduces the mass that needs to be launched from Earth for resupply, moving us from a fragile, dependent outpost to a resilient, self-sufficient homestead in space. It's a profound demonstration that sustainability is the key to survival, and that even the most mundane aspects of human existence, our waste, can be transformed into the very foundation of our longevity among the stars. This elegant solution for managing organic byproducts perfectly sets the stage for tackling the next great challenge, harnessing the immense thermal energy that floods the space environment, using the very same debris we've been trying to clear. Now, let's shift our focus from biological cycles to a more fundamental challenge of the space environment: the brutal and unrelenting swing between extreme heat and extreme cold. In space, there is no air to moderate temperatures, so an object in direct sunlight can soar to 250 degrees Fahrenheit, while the same object in shadow just moments later can plunge to -250 degrees. For a space station or a lunar base, these wild fluctuations aren't just uncomfortable, they're a direct threat to the integrity of equipment and the survival of a crew. Managing this thermal chaos is a constant, energy-intensive battle. But what if the solution was already drifting around us, waiting to be collected? This is the elegant concept behind using compressed space debris as thermal energy storage, a technology that turns hazardous scrap into a massive, orbital battery for heat. The principle at work here is one of the most basic in physics: thermal mass. Certain materials have a natural ability to absorb, store, and later release large amounts of thermal energy. Think of a thick stone wall in an old house. It soaks up heat from the sun during the day and slowly radiates it back into the room at night, keeping the temperature stable and comfortable. In space, the ideal material for this job is metal, specifically the aluminum and titanium alloys that make up the bulk of orbital debris. These metals possess an excellent combination of high thermal capacity and conductivity, meaning they can hold a lot of heat and transfer it efficiently. A large, solid block of this recycled metal acts like a thermal sponge, soaking up excess energy when the sun is blazing, and then metering it back out during the frigid orbital night. The process of creating these thermal batteries is a perfect fusion of recycling and utility. Robotic servicer craft would be tasked with collecting appropriate metallic debris panels from old satellite bodies, fragments of rocket fairings, and other sizable pieces. This material would be transported to an orbital processing facility where it is fed into a solar furnace, using focused sunlight to melt it down into a liquid state. In this molten form, any contaminants or non-metallic materials can be easily separated out, leaving a pure, homogeneous liquid metal. This is then poured into standardized, modular molds, perhaps simple, geometric shapes like bricks or larger, custom-designed panels. As it cools and solidifies in the microgravity environment, it forms a dense, solid block with consistent thermal properties, ready for its new job. These blocks are then integrated directly into the architecture of a space habitat or station. They wouldn't be hidden away, they would become a fundamental part of the structure itself. Imagine the outer walls of a lunar base module being lined with these recycled metal bricks. As the sun beats down on the base during the long lunar day, the bricks absorb that punishing heat, preventing the interior from becoming an oven. Then, when the 2-week-long lunar night begins and temperatures plummet, the bricks slowly release their stored thermal energy, radiating it inward to keep the habitat warm and stable. In an orbital station, a more active system could be used, with fluid loops running through channels in the blocks to transfer heat more precisely to where it's needed most. The advantages of this approach are immense, primarily in the form of mass savings. Launching dedicated, complex thermal control systems from Earth is incredibly heavy and expensive. These systems often rely on banks of batteries, heat pumps, and radiators, all of which add mass, complexity, and potential points of failure. By manufacturing the primary thermal mass in orbit from materials that are already there, we eliminate the need to launch that incredible weight. This system is also beautifully passive and reliable. There are no moving parts to break, no chemicals to leak, and no electrical systems to short out. It's a simple, elegant, and robust solution that leverages the inherent properties of material we once considered worthless. This transformation of dangerous clutter into a critical life support utility is a masterclass in pragmatic innovation, proving that the most effective solutions are often those that work in harmony with the environment, using its own resources to overcome its challenges. While we've explored using the bulk of space debris for everything from radiation shielding to thermal storage, some of the most valuable materials hiding within this orbital junkyard aren't the metals, but the advanced carbon-based composites. Think about the sleek, black panels that once formed the outer shells of satellites or the protective fairings that shielded delicate payloads during launch. These are often made from carbon fiber, reinforced polymers, and other sophisticated composites. Instead of seeing them as mere scrap, we can now envision them as the ultimate raw material for one of the most revolutionary substances of the 21st century, graphene. This is the promise of orbital graphene production, a technology that transforms what was once high-tech trash into a miracle material, and it does so by leveraging the one environment where it can be made best, the pristine vacuum and weightlessness of space itself. Graphene is a true wonder material. It's a single layer of carbon atoms arranged in a hexagonal lattice, and it's incredibly strong, about 200 times stronger than steel by weight, superbly conductive of both electricity and heat, and nearly transparent. Its potential applications are staggering, from revolutionizing electronics with ultra-fast, flexible chips to creating super-strong, lightweight composites for everything from cars to aircraft. But here on Earth, manufacturing high-quality graphene in large sheets is notoriously difficult and expensive. The process is often plagued by impurities and defects that form because of gravity's relentless pull, which causes layers to sag, crumple, or fold unevenly during production. This is where the microgravity environment of low Earth orbit becomes not just an advantage but a game changer. In the quiet, undisturbed conditions of space, those pesky gravitational forces simply vanish. Without convection currents to stir the air or sedimentation to cause heavier elements to sink, processes become incredibly calm and controlled. This allows for the exquisitely precise manipulation of individual atoms and molecules. When producing graphene, this means that carbon atoms can be deposited onto a substrate in a perfectly uniform, flawlessly flat layer, atom by atom. The result is graphene sheets of a quality, size, and purity that are virtually impossible to achieve in any terrestrial laboratory. This isn't just an incremental improvement, it's a leap into an entirely new class of material performance. Experiments aboard the International Space Station have already been paving the way for this, studying the fundamental principles of material synthesis in microgravity. Projects like the MISS series of experiments have exposed hundreds of material samples to the space environment for years, providing invaluable data on how things form and behave when freed from Earth's gravity, building the foundational knowledge needed for industrial-scale production. So, how would this orbital alchemy work? The process begins with the collection of carbon-rich debris. Specialized robotic craft would target specific defunct satellites known to have large composite structures, like antenna reflectors or entire body panels. These would be carefully grappled and transported to a dedicated orbital manufacturing facility. Inside, the real transformation begins, using intense, focused lasers or sophisticated solar furnaces that concentrate raw sunlight. The composite debris is vaporized. This controlled vaporization breaks down the complex polymers and resins, liberating the fundamental carbon atoms from their molecular bonds. These free-floating carbon atoms are then guided, perhaps using precise magnetic or electrostatic fields, onto a waiting substrate, a smooth, thin sheet of copper or nickel. There, in the perfect stillness of microgravity, they self-assemble into that coveted, perfect honeycomb lattice, growing layer by pristine layer into large sheets of flawless graphene. The potential applications for this space-made material are as vast as they are transformative. Back in orbit, this ultra-strong, lightweight graphene could be used to build the next generation of spacecraft vessels with hulls that are both feather-light and incredibly resilient to micrometeoroid impacts, or solar sails of immense size for propulsion. It could be integrated into the systems of space stations to create highly efficient, flexible heat dissipation systems or revolutionary electronics. But the impact wouldn't be confined to space. This high-value material could be packaged and safely returned to Earth, where it would command a premium price. Imagine it being used to create batteries that charge in minutes and last for days, or to build touchscreens that are virtually unbreakable, or to develop medical implants that are both stronger and more compatible with the human body. This moves the economic model of space debris recycling from a simple cost-saving measure into a high-value export industry, proving that cleaning up our orbital environment isn't just a responsibility, it can be a tremendously profitable venture. It stands as a powerful testament to the idea that our greatest innovations often come not from discovering new resources, but from learning to see the resources we've already discarded in a brilliant new light. Now consider the incredible eye in the sky that is the Hubble Space Telescope, an instrument that has fundamentally reshaped our understanding of the cosmos. Its beautiful, precisely ground mirror is a masterpiece of engineering designed to last for decades. But what happens when the telescope that carries it reaches the end of its operational life? Traditionally, we've thought of it as a single, retired unit, but a new vision is emerging, one where the most valuable part of that telescope, its pristine mirror, is given a second act far grander than its first. This is the promise of constructing new space-based observatories from salvaged mirror segments, a concept that treats orbit not as a graveyard for old technology, but as a hardware store for the next generation of cosmic discovery. The logic behind this is overwhelmingly compelling. The process of designing, grinding, polishing, and testing a large primary mirror for a space telescope is a monumental undertaking. It can take over a decade and consume a significant portion of a mission's entire budget. These optics are built to incredible tolerances. The primary mirror on the Hubble, for instance, is polished to an accuracy of 10 nanometers. That's about 1/10,000th the width of a human hair. This exquisite precision doesn't simply vanish when the satellite's onboard computer fails or its fuel runs out. The mirror itself, protected in the vacuum of space from the weathering and contamination it would face on Earth, often remains in near-perfect condition, a sleeping giant waiting for a new purpose. Many decommissioned telescopes, including some that were predecessors to or contemporaries of Hubble, are drifting in graveyard orbits, their incredible optical hearts still silently perfect. Realizing this vision requires a new era of in-space servicing and assembly, a field that is rapidly moving from science fiction to reality. Projects spearheaded by NASA, such as the ongoing research into the on-orbit servicing, assembly, and manufacturing missions, are actively developing the tools and techniques needed for this delicate work. The process would begin with a sophisticated robotic servicer craft, equipped with advanced vision systems and incredibly dexterous arms, rendezvousing with a chosen retired telescope. Its first task would be a meticulous inspection, using lasers and sensors to map the mirror's surface and confirm its structural and optical integrity. Then, with painstaking care, the robotic arms would set to work. they would need to unfasten the complex fittings and actuators that hold the mirror in place, a task requiring a gentle touch and immense precision to avoid imparting any stress or damage to the glass. Once carefully extracted, the mirror segment would be transported to an orbital clean room facility, perhaps a specialized module on a future space station or a free-flying platform. Here, it would undergo a thorough cleaning process, likely using gentle techniques like ultraviolet light or atomic oxygen to remove any microscopic contaminants that may have accumulated over years in space without scratching or damaging the sensitive coatings. The final and most critical step is calibration and integration. The salvaged mirror would be robotically mounted into a brand new framework, one designed to hold not just one, but multiple such segments, aligning them to act as a single, colossal light-gathering surface. This new framework would be outfitted with a new suite of state-of-the-art sensors, cameras, and spectrographs, technology that would have advanced tremendously since the original mirror was launched. The scientific payoff is almost beyond imagination. By combining multiple large salvaged mirrors, we could effectively assemble an observatory in space with light-collecting area far larger than anything we could afford to launch in one piece from Earth. This giant eye could peer deeper into the universe than ever before, directly imaging Earth like planets orbiting distant stars, unraveling the mysteries of dark matter and dark energy, and watching the first galaxies form at the dawn of time. It dramatically reduces the cost and risk of doing bold, new astrophysics. Launching a large, monolithic mirror is a nerve-wracking endeavor. The slightest vibration or anomaly during ascent can ruin a billion-dollar instrument. By building large structures in space from smaller, proven components, we sidestep that risk entirely. This approach creates a powerful legacy system, where each generation of telescopes literally builds upon the hardware of the last, creating a continuous, ever-expanding window on the universe. It's a beautiful cycle of renewal, proving that in the pursuit of knowledge, even our retired tools can help us see further than we ever dreamed possible. While we often marvel at the large structures and metallic shells of satellites, some of the most valuable treasures are hidden deep within their electronic hearts. Tucked away inside the husks of retired communications and imaging satellites are sophisticated circuit boards, processors, and sensor arrays, components rich with high-purity silicon, germanium, and gallium arsenide, the fundamental building blocks of the digital age. Instead of viewing this sophisticated e-waste as mere clutter, we can now imagine it as the seed stock for a revolutionary new industry, orbital semiconductor manufacturing. This concept pushes the idea of recycling into the realm of high-precision alchemy, transforming the discarded brains of old satellites into the next generation of ultra-powerful computing technology, all within the one environment that offers a unique and profound advantage, the perfect silence of microgravity. The magic of a microchip lies in its crystalline structure. On Earth, the process of growing the large, flawless silicon crystals needed for advanced processors is a constant battle against gravity's relentless pull. As the crystal is slowly drawn from a molten vat of silicon, convection currents within the liquid cause subtle fluctuations in temperature and composition. Gravity also induces stresses that can lead to tiny imperfections called dislocations in the crystal lattice. These microscopic defects are the enemy of performance. They can impede the flow of electrons, generate heat, and ultimately limit the speed and efficiency of the final chip. In the weightless environment of space, these problems simply vanish. Without gravity to cause convection or sedimentation, the molten silicon remains perfectly still and uniform. This allows for the growth of crystals of unprecedented size and perfection, with a molecular structure so orderly it's virtually impossible to achieve on our planet. The result is a base material that is fundamentally superior, paving the way for semiconductors that are faster, more energy efficient, and capable of handling far greater thermal loads than their terrestrial counterparts. This isn't a distant fantasy, it's a field of active and promising research. Studies and experiments dating back to the Skylab missions in the 1970s have consistently demonstrated the advantages of microgravity for material processing. More recently, commercial entities like Space Tango and established aerospace players have been sending compact manufacturing modules to the International Space Station to test the production of various materials, including optical fibers and protein crystals, with an eye toward semiconductors. The results have been compelling, showing that the quality and performance of materials grown in space can be orders of magnitude higher. This research is building the foundational knowledge needed to scale up from small experiments to full-scale industrial production in dedicated orbital facilities. The process of turning a derelict satellite into a state-of-the-art microchip is a symphony of precision robotics and advanced chemistry. It begins with a specialized servicing craft, equipped with fine manipulators more akin to a surgeon's tools than a mechanic's wrench, carefully docking with a target satellite. The robot would first need to gain access to the vehicle's internal avionics bay, a task requiring custom solutions for each satellite model. Once inside, it would use advanced computer vision and laser scanning to identify and map the most valuable components, specific processor units, memory modules, and sensor chips known to contain high-purity materials. These components are then meticulously desoldered and extracted using precise thermal and mechanical tools to avoid contamination. Back at an orbital fabrication facility, the real transformation begins. The salvaged components are fed into a high-temperature furnace where they are vaporized, breaking them down to their elemental constituents. Sophisticated purification systems, which could utilize fractional distillation or zone refining in the absence of gravity-driven mixing, then separate out the ultra-pure silicon, germanium, and other dopant elements from any impurities or base metals. This purified feedstock is then ready for the crystal growth process, using a technique like chemical vapor deposition inside a specialized microgravity chamber. The pure silicon is deposited atom by atom onto a seed crystal, slowly building a massive, flawless ingot of single crystal silicon. This pristine ingot is then sliced into impossibly thin wafers, which become the canvas for the next step. Using focused ion beams or extreme ultraviolet lithography, the intricate nanoscale circuits are etched onto the wafer's surface, layer by layer, creating microchips of unparalleled complexity and performance. The applications for these space-forged semiconductors are as vast as they are transformative. In orbit, they would be immediately integrated into the next generation of satellites and deep space probes, creating thinking machines that are exponentially more powerful and reliable, capable of handling autonomous navigation and complex data analysis without the constant need for guidance from Earth. But the impact would undoubtedly ripple back to our planet. These chips could be carefully packaged in reinforced capsules and returned to Earth, where they would revolutionize fields that demand absolute performance. Imagine the supercomputers modeling climate change or simulating complex molecular interactions for drug discovery, powered by processors free from the flaws that limit their terrestrial cousins. The aerospace, medical imaging, and artificial intelligence industries would eagerly seek out this new class of hardware, creating a high-value economic return that helps fund the entire orbital recycling ecosystem. This endeavor beautifully demonstrates that the value hidden within space debris isn't just in its bulk mass. It's in the incredible purity and potential of the materials we so carelessly abandoned, waiting to be reclaimed and reborn into something extraordinary. But tracking this chaotic sea of fragments presents a challenge of almost unimaginable scale. How do you manage a field of 128 million objects, each on its own unpredictable path? The answer lies not in building more powerful telescopes or radar stations, but in developing a smarter, more intuitive way to understand the data we already collect. This is where artificial intelligence, specifically neural networks, enters the picture, acting as a digital brain to make sense of our orbital environment. Imagine a sophisticated AI system, a digital cartographer that doesn't just plot points on a map, but actually learns the intricate patterns, relationships, and hidden rhythms of space debris. It analyzes the immense, ever-changing flow of data, from ground-based radar pings to telescope observations, and begins to see the orbital highway not as a random cloud, but as a complex system with predictable behaviors and emergent patterns. This technology is already moving from the theoretical to the operational. The European Space Agency's Space Debris Office, for instance, is a world leader in this field, employing advanced software to constantly monitor and model the debris environment. Their systems ingest terabytes of tracking data daily, but the next evolutionary step involves machine learning algorithms that can do far more than just catalog. A neural network designed for this task is trained on historical data, learning from decades of observed collisions, near misses, and orbital decay patterns. It begins to understand how a piece of debris with a certain mass, shape, and composition will behave over time, factoring in subtle influences like the slight but constant drag of the upper atmosphere or the gentle but persistent push of solar radiation pressure. This allows it to forecast potential collisions with a degree of accuracy far beyond traditional linear models, issuing early warnings for conjunctions that might have otherwise been missed. The process itself is a fascinating application of modern computing. Vast datasets containing the positions, velocities, and estimated properties of millions of objects are fed into the neural network. The algorithm doesn't just crunch numbers, it identifies complex, non-linear correlations. It might learn, for example, that certain types of debris in sun-synchronous orbits are more likely to experience unpredictable tumbling during specific solar cycles, or that clusters of fragments from a particular breakup event tend to disperse in a statistically predictable way. This continuous learning loop means that with every new observation, every confirmed close approach, the network gets smarter, its predictions sharper, and its confidence higher. This transforms the overwhelming, paralyzing problem of tracking millions of objects into a manageable exercise in intelligent resource allocation. Instead of wasting precious observation time and fuel on low-probability threats, cleanup missions can be directed with surgical precision towards the most dangerous pieces of debris or the most valuable targets for recycling. This represents a brilliant fusion of digital and physical recycling. We are not only mining the physical materials from the orbital junkyard, but also mining the immense value hidden within the data generated by that junk. The debris itself becomes a source of information, teaching our algorithms how to better manage the environment it litters. This intelligence-driven approach is the essential nervous system for the entire ecosystem of technologies we've explored, the coordinating intelligence that will allow autonomous systems to operate safely and efficiently in the crowded skies above us. It provides the situational awareness necessary for robots to navigate, for harvesters to prioritize their targets, and for factories to plan their production, setting the stage for the next logical and most transformative step in this evolutionary chain. Systems that can not only think for themselves but also build copies of themselves. Now, let's push the boundaries of imagination to their absolute limit with a concept that feels less like engineering and more like nature itself taking over: self-replicating robotic swarms. This is the ultimate expression of a closed-loop system in space, where the cleanup machines don't just consume debris for fuel or materials, they use it to literally build copies of themselves. Envision a single, pioneering robotic craft, launched from Earth with a simple but monumental mission: to find, process, and replicate. It's the seed from which an entire forest of cleaners could grow, a vision of exponential growth that could finally match the scale of the debris problem itself. This idea draws its inspiration from a theoretical concept proposed by the legendary mathematician John von Neumann back in the 1940s, the idea of a self-replicating automaton, a machine capable of creating a perfect copy of itself given the right raw materials. For decades, this remained a fascinating thought experiment, a staple of science fiction. But now, with the advent of advanced robotics and in-space manufacturing, we are inching toward a future where this powerful idea could be applied to one of our most pressing practical challenges. The process would be a breathtaking display of autonomous efficiency. That first seed robot, let's call it a progenitor unit, arrives in a densely cluttered orbital region. Its first task is survival and replication. Using its own suite of tools, likely a combination of robotic arms, cutting lasers, and grinding mechanisms, it carefully captures a suitable piece of debris, perhaps a derelict satellite packed with valuable metals and electronics. It doesn't just collect this junk, it begins a precise disassembly process, sorting the materials by type. Aluminum trusses are fed into a furnace to be melted down into feedstock for a 3D printer. Silicon chips and copper wiring from old circuit boards are carefully extracted and cleaned for reuse in new computational systems. The robot is essentially acting as a carnivorous creature, digesting its prey and using the nutrients to grow. Then the magic happens. Following a digital blueprint stored in its memory, the robot's internal 3D printer begins fabricating the components for a new version of itself. A new chassis, new joint assemblies, new structural members. Simultaneously, it refurbishes the salvaged electronics, testing and integrating them into the new design. Finally, using its own robotic arms, it begins the meticulous assembly process, putting together the pieces of its offspring. Once the new unit is complete and activated, it boots up, runs its own diagnostics, and then detaches from its parent. Now there are two. Those two then set out to find more debris, each creating another copy, and so on and so on. The growth isn't linear, it's exponential. 2 become 4, 4 become 8, and within a surprisingly short number of cycles, a small army of these robots could be at work, their numbers limited only by the availability of raw material, which, in this case, is the very problem we need them to solve. The potential of this technology to revolutionize orbital sustainability is almost beyond measure. A single launch could theoretically lead to a cleanup capacity that grows to meet the challenge in real time, instead of requiring an endless series of expensive and slow follow-up missions. It could make the dream of fully clearing certain orbital lanes within a few decades a tangible reality rather than a distant hope. This represents the pinnacle of turning trash into functional labor. The debris is no longer just a resource for building structures or fuel, but for building the very workforce that will eliminate it. It's a profoundly elegant and efficient solution, a true closed loop where the problem actively enables its own solution. However, a concept this powerful inevitably comes with profound ethical and technical challenges that must be addressed with extreme caution. The most obvious fear is the classic gray goo scenario, where a loss of control over the replication process leads to an unstoppable, exponentially growing swarm that consumes everything in its path, including functioning satellites. Preventing this requires incredibly robust fail-safes programmed directly into the core of each robot's operating system. These could include hard limits on the number of generations a unit can produce, strict programming that only allows replication from certain approved types of non-functional debris, and built-in self-destruct mechanisms that activate if a unit ever goes out of a predefined communication range or fails to receive a regular, all-clear signal from human controllers on Earth. Furthermore, the technical hurdles are immense. Creating a robot that can perform such complex and varied tasks, from precision machining to delicate electrical work, entirely autonomously in the harsh environment of space, is a monumental feat of engineering that pushes the boundaries of what's possible today. Yet, it's this very act of pushing boundaries that has always driven our greatest achievements in space, turning the impossible into the inevitable through a combination of vision, patience, and brilliant engineering. But what if the very clutter we're trying to clear could become the fuel for our next great leap into the solar system? This idea pushes the boundaries of orbital mechanics into the realm of pure creative genius, treating space debris not as waste, but as a network of gravitational stepping stones. We're all familiar with the concept of a gravity-assist spacecraft stealing a tiny bit of momentum from a massive planet like Jupiter to fling itself toward the outer solar system. It's a well-established technique that saves immense amounts of fuel and time. Now apply that same principle, but on a much smaller and more precise scale, using the countless pieces of human-made debris already in orbit. The concept is audacious. Why wait for the rare, perfect alignment of planets when we can create our own miniature gravity wells from the junk we've left behind? The physics, while complex, is undeniably sound. Every single object with mass exerts a gravitational pull, no matter how small. A spent rocket booster or a large derelict satellite might seem insignificant compared to a gas giant, but in the delicate balance of orbital mechanics, its influence is far from zero. For a carefully calibrated mission, a close flyby of such an object could provide just enough of a nudge, a tiny change in velocity, to alter a spacecraft's trajectory meaningfully. Over the course of a long journey, a series of these meticulously planned micro-assists could add up to a significant boost, saving propellant that would otherwise be needed for course corrections and enabling missions to reach farther destinations or carry more scientific instruments. Turning this theoretical possibility into a practical reality requires a symphony of advanced technology and precise calculation. The first and most critical component is an exquisitely detailed catalog. We're not just talking about knowing an object's position. We need to know its mass distribution, its shape, and its rotational state with incredible accuracy. This level of detail goes far beyond simple tracking for collision avoidance. Advanced radar imaging and laser ranging from future space-based observation platforms would be essential to build this high-fidelity gravitational map of the orbital junkyard. With this map in hand, sophisticated navigation algorithms powered by artificial intelligence could then get to work. These programs would analyze a spacecraft's intended destination and compute the most efficient path, weaving through the orbital environment to use a series of designated debris objects as gravitational pivot points, each one tweaking the trajectory ever so slightly toward the final goal. Imagine a small, low-cost probe destined for a rendezvous with a near-Earth asteroid. Instead of launching with a large and expensive propulsion system, it carries just enough fuel for minor adjustments. Its computer is loaded with the latest gravitational map of low Earth orbit. Shortly after deployment, it executes a short burn to align itself for a close pass by a known, massive object, perhaps the discarded upper stage of a heavy-lift rocket. It doesn't need to dock or even slow down. It simply swings within a few hundred meters. The rocket stage's minuscule gravitational tug, combined with the probe's high speed, bends its path ever so slightly, like a stone skipping across the top of a pond. This first micro-assist is just the beginning. The probe's trajectory is now set for a second encounter with another piece of debris in a higher orbit, which gives it another small push, and so on, until it has built up enough combined velocity change to break free on its intended path, having used the forgotten artifacts of past missions as its launch pad. This approach represents a complete inversion of our current relationship with space debris. It transforms a passive hazard into an active, utilitarian resource. These objects become more than just targets for removal. They become strategic assets, fixed points in the orbital landscape that can be used to navigate more efficiently. It's a concept that embodies the ultimate in space sustainability, finding a functional purpose for every single piece of material, no matter how small its influence might be. This clever application of fundamental physics demonstrates that with enough ingenuity, there is no such thing as true waste in space, only resources we haven't yet learned how to use. This mindset, which finds gravitational utility in discarded mass, naturally prepares us to consider an even more tangible application, using the largest pieces of this orbital inventory as literal building blocks for the next generation of space infrastructure. While the idea of building massive solar farms in space has captivated scientists for decades, the sheer cost of launching thousands of tons of material into orbit has always been the dream's greatest obstacle. But what if the answer wasn't launching new infrastructure, but repurposing what we've already sent up? This is the powerful logic behind using the skeletons of defunct satellites and spent rocket stages as the foundational scaffolding for orbital solar power stations. These derelict structures represent a colossal, pre-launched, and fully paid-for investment in space-worthy engineering. Their frames and trusses were meticulously designed to survive the violent vibrations of a rocket launch and the brutal temperature swings of the space environment. They are, in essence, perfectly engineered skeletons waiting for a new purpose. By viewing them not as trash but as prefabricated real estate, we can completely reframe the economics of space-based solar power. The process for this cosmic retrofit is a masterclass in practical engineering. Imagine a future where autonomous robotic servicer craft, equipped with advanced tools and vision systems, are dispatched to graveyard orbits. Their targets are the large, derelict communication satellites and the empty hulls of rocket upper stages that have completed their missions. The first task is a meticulous survey, using lasers and sensors to create a high-resolution digital model of the derelict structure, assessing its integrity and stability. Once deemed sound, the real work begins. Using precision-cutting tools, the robots would carefully remove any obsolete or damaged components, old antenna dishes, thruster modules, and avionics boxes, effectively stripping the structure down to its bare, robust frame. This creates a clean, blank canvas of high-strength aluminum and titanium trusses. Next comes the retrofitting phase. From a supply depot or delivered by a separate launch, the robot receives compact rolls of advanced, ultra-lightweight solar film and new power transmission equipment. Unlike the heavy, rigid solar panels of the past, this new generation of photovoltaics is flexible and incredibly efficient. The robotic arms, guided by their digital blueprint, would unfurl these massive sheets and methodically attach them to the old satellite's frame, effectively dressing the skeleton in a new skin of energy-generating material. The existing structure's own power conduits could even be cleaned and repurposed to help channel the electricity. Finally, a new, compact microwave or laser transmitter would be installed, turning the entire assembly into a functional power station, ready to beam gigawatts of clean energy back to receiving stations on Earth. This vision is actively being pursued by nations serious about their energy future. Japan's space agency, JAXA, has been a long-time pioneer in this field with its Space Solar Power Systems, or SSPS project. Their roadmap involves developing the necessary technologies for beaming power from orbit, with the ultimate goal of constructing a massive 1-gigawatt solar power station. While their plans currently call for new construction, the principles of in-space assembly and robotic integration they are developing are directly applicable to a repurposing model. The key advantage is staggering cost reduction. By eliminating the need to launch the primary structure, often the heaviest part, the financial and environmental barriers to space-based solar power crumble. This approach doesn't just make the technology feasible, it makes it inevitable, accelerating our transition to a post-scarcity energy model by decades. It proves that our path to a sustainable future isn't always about inventing something brand new, but often about looking at the resources we already have with more imaginative and ambitious eyes. This pragmatic merger of past missions and future needs creates a powerful legacy system where the infrastructure of yesterday directly enables the prosperity of tomorrow. But the value of these retired sentinels doesn't end when their primary mission is complete. Many of these instruments, though perhaps no longer suited for their original high-precision scientific tasks, remain perfectly capable of collecting valuable data when recalibrated and refocused. This is where a powerful new vision emerges, a distributed network of environmental guardians crafted not from new launches, but from the carefully chosen eyes and ears of our orbital past. Imagine a constellation of these repurposed sensors, strategically positioned to create a comprehensive, real-time monitoring system for the entire planet. A spectrometer from a retired weather satellite could be reprogrammed to specifically track the dispersal of methane plumes from industrial areas or major agricultural regions. An aging high-resolution imager could be tasked with monitoring the health of coral reefs, detecting the subtle bleaching events that signal distress long before they become catastrophic. This isn't just about giving old hardware a new job. It's about building a planetary-scale immune system, using the very technology we once used to simply observe the Earth to now actively protect it. This concept of intelligent reuse is deeply embedded in the culture of agencies like NASA. Their Earth Science Division has a long and successful history of extending missions and finding new applications for existing assets. The remarkable story of the GRACE mission, the Gravity Recovery and Climate Experiment, is a perfect example. Its twin satellites were designed to map Earth's gravity field, but the data proved invaluable for tracking massive changes in groundwater storage, ice sheet mass, and even deep ocean currents. When the original GRACE satellites reached the end of their life, NASA and its partners didn't abandon the research. They built and launched GRACE follow-on, continuing that critical data record. The leap we're discussing now takes that philosophy a step further, moving beyond building replacements to actively reanimating the existing fleet of retired observers already in space. Initiatives are already underway to develop the robotic servicing technologies needed to make this a reality, proving that the will and the ingenuity exist to turn this vision into operational fact. The technical process of this transformation is a fascinating blend of robotic precision and digital rebirth. It begins with a servicing vehicle, equipped with advanced grasping tools and protective shielding, carefully rendezvousing with a designated retired satellite. The target isn't the whole spacecraft, but its specific sensory organs. Using laser scanners and high-definition cameras, the robot creates a detailed three-dimensional map of the satellite's exterior, identifying the mounting points and connectors for the desired instrument, perhaps a multi-spectral imager or a laser rangefinder. With surgical precision, robotic arms then set to work unfastening bolts, disconnecting data and power lines, and finally detaching the entire sensor package from its aging host. This salvaged instrument is then transported to a safe holding area, where it undergoes a thorough diagnostic check to assess its health after years of inactivity in the harsh space environment. The real magic happens next through software. The instrument's onboard computer is wiped and reloaded with new, purpose-built algorithms. These aren't the complex codes for its original 15 different scientific functions. This is a streamlined, focused program designed to do one or two things exceptionally well. A sensor that once spent its processing power on atmospheric correction and cloud filtering might be reprogrammed to do nothing but scan coastlines for oil slicks or algal blooms, dramatically increasing its efficiency for that specific task. Its calibration is meticulously adjusted, fine-tuning its sensitivity to the exact wavelengths of light that indicate the presence of specific pollutants like nitrogen dioxide or sulfur dioxide. Once this digital rebirth is complete, the instrument is no longer a general-purpose observer. It has become a dedicated sentinel, a specialist in its new environmental protection role. It is then integrated into a new, simpler satellite bus, perhaps itself built from other recycled components, and deployed into an optimal orbit to begin its second life, feeding a continuous stream of vital data into a global network dedicated to planetary health. This creates a powerful and poetic closure of the loop, where technology originally launched to study our world is now being used directly to safeguard it, demonstrating that our greatest tools for solving Earth's problems might already be floating above us, just waiting for a new command. Now, let's expand our vision from protecting assets in orbit to safeguarding the entire planet itself. Consider the most apocalyptic of scenarios, a sizable asteroid or comet on a direct collision course with Earth. For decades, the stuff of science fiction, this threat is taken with utmost seriousness by the world's space agencies. The standard proposed solution often involves launching a dedicated spacecraft to intercept the object, either to blow it apart with a nuclear device or, in a more nuanced approach, to nudge it gently off course. But launching such a mission on short notice is a monumental challenge, requiring a rocket to be ready to go at a moment's notice, a hugely expensive proposition. But what if our first line of planetary defense wasn't waiting on a launch pad, but was already strategically positioned in space? This is the astonishing premise of using large pieces of space debris, like the empty hulls of spent rocket bodies, as physical shields or gravitational tugboats to deflect an incoming celestial threat. The concept draws direct inspiration from one of the most successful planetary defense experiments in history, NASA's Double Asteroid Redirection Test, or DART mission. In 2022, a refrigerator-sized spacecraft was deliberately crashed into a small moonlet called Dimorphos, which orbits a larger asteroid named Didymos. The goal wasn't to destroy it, but to kinetically impact it, to give it a slight push. The results were stunningly successful, altering the moonlet's orbit and proving that we can, in fact, change the trajectory of a celestial body. Now imagine applying that exact same principle, but instead of building and launching a dedicated impactor, we repurpose one that's already up there. A spent upper stage from a heavy lift rocket drifting in a graveyard orbit possesses two key attributes: significant mass and a pre-launched status. That mass is the critical factor. In the physics of deflection, the change in velocity imparted to an asteroid is a function of the mass and speed of the impactor. A large rocket body, which can weigh several tons, could deliver a potent kinetic punch. The process of turning this dormant hazard into a planetary guardian would be a breathtaking feat of coordination and engineering. It begins with early warning. Ground-based telescopes and upcoming space-based sentinels like the NEO Surveyor would first identify a potential threat, calculating its trajectory years or even decades in advance. Once a dangerous object is confirmed, mission planners would turn to a meticulously curated catalog of orbital debris, searching for the ideal candidate. They wouldn't just be looking for any large piece of junk. They'd need one with the right mass in the right orbital neighborhood that could be economically moved into an interception path. A suitable spent rocket body, perhaps from a decades-old lunar mission, would be identified. The next step is mobilization. A relatively small, fast pit crew spacecraft would be launched from Earth. Its sole mission is to rendezvous with this dormant rocket stage and outfit it for its heroic final journey. This involves attaching a compact but powerful propulsion module and a sophisticated guidance system to the inert hull. Once this new propulsion unit is secured and activated, the former piece of space trash is transformed. It's no longer debris, it's now a kinetic impactor. Guided by teams on Earth, it fires its engines, slowly but surely pushing itself out of its graveyard orbit and onto a new, calculated trajectory, a long, looping path designed to intercept the incoming asteroid with pinpoint accuracy. The final act is one of silent, brutal physics. Traveling at immense speed, the repurposed rocket body slams into the asteroid. Just like the DART impactor, it doesn't need to vaporize the threat. It simply needs to transfer its momentum, giving the asteroid a tiny but crucial nudge. Over the months and years that follow, that tiny alteration in velocity compounds, pushing the asteroid's path just enough to ensure it misses Earth entirely. It's a staggering example of cosmic jujitsu, using the mass and position of our own discarded hardware to neutralize a threat from the depths of space. This transforms the narrative of space junk from one of careless pollution to one of unintended preparation, suggesting that our greatest mistakes in orbit might one day provide the raw material for our most profound acts of planetary salvation. Yet beyond the critical work of planetary defense and environmental monitoring, there exists a profoundly human dimension to this story, one that transforms cold, hard machinery into a canvas for our collective memory and aspiration. Imagine a future where the most iconic pieces of our orbital past are not hauled away for scrap, but are instead carefully curated and assembled into breathtaking sculptures that float silently against the backdrop of the cosmos. These wouldn't be mere collections of junk. They would become the first orbital museums, celestial galleries celebrating the human spirit of exploration. Picture a recognizable solar panel from the historic Vanguard 1 satellite, the oldest human-made object still in space, mounted alongside a window from the decommissioned Mir space station. Together, they form a silent monument, a constellation of artifacts that tell the story of where we've been and hint at where we might go next. This vision moves the conversation about space debris beyond practicality and into the realm of poetry, where trash is reimagined as cultural treasure. The potential for public engagement and education is immense. These artistic installations could become pilgrimage sites for a new era of space tourism. Imagine a commercial space station arranging tours that allow visitors to don suits and gently float through a carefully arranged sculpture garden of space history, reaching out to touch the very hardware that paved the way for their own journey. For those of us still on Earth, powerful new generations of telescopes, both amateur and professional, could be trained on these exhibits. They would appear not as indistinct points of light, but as structured, sun-glinting assemblages, their changing silhouettes against the sun and moon becoming a new form of public celestial event. Schools could host viewing parties, tracking the passage of these cultural satellites much like stargazers once tracked Sputnik. This transforms the abstract and often invisible problem of space debris into a tangible, visible, and inspiring narrative, fostering a global sense of ownership and responsibility for our shared orbital environment. This is not a new or far-fetched idea. Artists have been dreaming of placing works in space for decades. In 1993, artist Arthur Woods realized this dream with his project, The Cosmic Dancer. This sculpture, a geometric form specifically designed for the weightless environment, was actually sent to the Mir space station, where it was installed by a cosmonaut crew. For the first time, a work of art was consciously experienced in orbit, demonstrating that human creativity has a place beyond our atmosphere. Woods's project proved that art could thrive in microgravity and that its presence could have a profound impact on those living in the isolation of space, providing a touchstone to humanity and culture. His pioneering work provides both a technical and philosophical blueprint for the larger-scale artistic reuse of space debris, showing that the desire to create beauty is a fundamental part of our drive to explore. The process of creating these orbital monuments would be a fascinating fusion of historic preservation, artistic vision, and advanced robotics. It begins with a meticulous archaeological survey of space, using historical records and advanced scanning to identify pieces with significant heritage value. A specialized robotic servicer craft, perhaps operated by a consortium of museums and space agencies, would then be dispatched to carefully retrieve these artifacts. The capture process would need to be incredibly gentle, using custom-designed fixtures to secure fragile, aging structures without causing further damage. Once secured, the items would be transported to an orbital atelier, a creative workshop in space. Here, under the guidance of artists and historians working remotely from Earth, robotic arms would begin the delicate work of assembly. Components might be welded, bolted, or even magnetically joined into a predetermined design, one that respects the individual history of each piece while forming a new, cohesive whole. The final sculpture would then be gently nudised into a stable, high-altitude orbit, ensuring its preservation for centuries to come as a permanent part of humanity's cultural legacy in space. This ambitious endeavor does more than just clean up orbit. It performs a vital act of symbolic alchemy. It transforms the narrative of space debris from one of pollution and carelessness into one of heritage and stewardship. A piece of a retired satellite is no longer just hazardous clutter. It becomes a relic, a touchstone connecting us to the countless engineers, scientists, and dreamers who made the space age possible. These orbital installations become permanent reminders of our capacity for both creation and neglect, and our growing responsibility to correct our mistakes. They foster a powerful sense of intergenerational continuity, honoring the achievements of the past while clearly signaling our commitment to a more sustainable and thoughtful future in the cosmos. This cultural repurposing completes the picture, proving that the value of what we leave in space isn't just measured in materials or energy, but in meaning. Think of the most powerful telescope on Earth, its giant mirror pointed at the depths of the universe, gathering photons that have traveled for millions of years. For its observations to mean anything, for the data to be trusted, its instruments must be perfectly tuned and its pointing must be absolutely precise. The slightest miscalibration can turn a groundbreaking discovery into meaningless noise. This relentless pursuit of accuracy is a constant challenge for astronomers and space trackers alike, and it turns out that one of their greatest tools for achieving it has been silently drifting overhead all along. We're talking about using the vast inventory of space debris itself as a cosmic calibration target, a way to turn a chaotic problem into a precise solution. This is a beautifully counterintuitive application where the very objects that clutter our view become the essential reference points that make that view clear and reliable. The principle is deceptively simple. To ensure any measuring instrument is accurate, you first test it against something you already know with absolute certainty. A chef uses a calibrated scale, a carpenter a trusted level. For a radar system tracking space debris or a telescope measuring the brightness of stars, you need a known object in the sky, something whose size, shape, orbit, and reflective properties are so well documented that any deviation in your reading immediately tells you about an error in your own equipment, not a change in the target. This is where retired space hardware becomes invaluable. A specific defunct satellite, for instance, is a perfect candidate. We know exactly what it's made of: its aluminum shell, its solar panels, its precise dimensions because we built it. We know its exact orbit because we tracked it meticulously during its operational life. It's a known quantity, a stable and predictable benchmark against which everything else can be measured. This practice isn't entirely new. Astronomers have long used the predictable passes of operational satellites like the Iridium constellation, which produced brilliant flashes known as iridium flares for calibration. But as those older satellites are decommissioned, a new standard is emerging from the graveyard orbits. The process of formalizing this turns ad hoc practice into a systematic science. Specific pieces of debris are officially designated as calibration standards by international bodies like the Inter-Agency Space Debris Coordination Committee. These aren't chosen at random. The ideal candidates are large, stable objects with simple, geometric shapes and surfaces that reflect light or radar waves in a consistent, well-understood way. A spent rocket body, a cube-shaped satellite, or a large panel that hasn't begun to tumble unpredictably are prime candidates. Their orbits are then monitored with extreme precision by a global network of sensors, refining their trajectories down to a matter of meters. The calibration procedure itself is a masterclass in precision. For a ground-based radar station, the operators will wait for a scheduled pass of their designated calibration target. As this known object arcs across the sky, the radar locks on, painting it with electromagnetic energy. The system knows exactly what the return signal should look like based on the object's known size and composition. If the returning signal is slightly off in strength, it indicates the radar's transmitter or receiver needs adjustment. If the calculated position is consistently a few meters off, it reveals a tiny error in the radar's pointing angle or timing systems. These minute errors are then digitally subtracted from all subsequent tracking data, ensuring that the readings for unknown, hazardous debris are razor-sharp and trustworthy. For optical telescopes, the same principle applies. They image the calibration satellite, measuring its brightness. Since scientists know exactly how bright it should appear at that specific distance and phase angle, they can correct their instruments to ensure that when they measure the light from a distant galaxy, that measurement is scientifically valid. This application creates a powerful, self-improving cycle. The better we can calibrate our sensors using these known objects, the more accurately we can track all the other, unknown pieces of debris. This enhanced tracking data, in turn, improves our orbital models and collision predictions, making space safer for everyone. It's a deeply elegant and pragmatic solution, using the problem to solve the problem. It proves that in the meticulous world of science and observation, there is no such thing as a truly useless object, only an unexploited property. A piece of space junk is no longer just a hazard. It's a fixed point of reference in a moving sky, a tool that ensures our view of the final frontier remains crystal clear. This relentless drive for precision and clear data is the very foundation upon which our next idea is built, a technology that demands the utmost accuracy to function. Now, let's dive into one of the most secure and futuristic applications emerging from our orbital scrap heap: quantum communication. Imagine a global network where sensitive data, from financial transactions to diplomatic messages, is transmitted with near-perfect security, protected by the fundamental laws of physics rather than just complex mathematics. This is the promise of quantum encryption, and it relies on a delicate dance of photons sent between precisely aligned antennas in space, the incredible part. The very hardware needed to build this network might already be orbiting above us, hidden within the skeletons of retired satellites. These old communication dishes and receivers, once used for broadcasting television signals or relaying phone calls, are now being seen in a brilliant new light, not as obsolete junk, but as the perfect foundation for the next generation of unhackable communication relays. The core principle behind quantum communication is both elegant and unbreakable. It relies on a phenomenon called quantum key distribution. In simple terms, a sender, often called Alice, transmits a stream of individual photons, particles of light, to a receiver, Bob. These photons are prepared in specific quantum states, representing the bits of a secret key. Here's the magic: according to the laws of quantum mechanics, any attempt to eavesdrop on this transmission inevitably disturbs the state of these photons. Bob and Alice would immediately detect this disturbance, revealing the presence of an intruder and causing them to discard the compromised key. This makes the system inherently secure. It's not that the encryption is hard to break, it's that the act of trying to listen in itself creates an undeniable alarm bell. However, this incredible security comes with a major challenge. These fragile quantum signals can only travel so far through the Earth's atmosphere or through fiber optic cables before they degrade and are lost. To create a truly global quantum network, we need to place the critical relay points in space, above the distorting veil of the atmosphere. This is where our orbital debris enters the story as an unexpected hero. Establishing a network of quantum relays from scratch would be astronomically expensive, requiring the launch of numerous large, delicate antennas and their precise pointing systems. But we've already unintentionally launched a great deal of this infrastructure over the past several decades. Many decommissioned communication satellites have large, high-quality parabolic antennas and sophisticated receivers that were designed for precisely capturing and transmitting faint microwave signals. While they weren't built for quantum purposes, their fundamental capability to send and receive precise electromagnetic signals with high fidelity makes them ideal candidates for retrofitting. Their structures are already in orbit, already stabilized, and already paid for. The pioneering work in this field, demonstrated by projects like China's MISHA satellite, has proven the core technology. MISHA successfully conducted the first quantum-secured video call between continents and performed groundbreaking experiments in quantum entanglement distribution, all from its orbital perch. It showed the world that space-based quantum communication is not just theory, but a working reality. The process of transforming a piece of forgotten debris into a cutting-edge quantum node is a fascinating blend of robotic precision and technological upgrade. A specialized servicer spacecraft would first rendezvous with a designated Defunct satellite, one known to have a large, intact antenna dish. Using advanced tools, it would carefully detach this entire assembly, along with its supporting gimbals and pointing mechanisms from the old satellite body. This salvaged hardware would then be transported to an orbital facility where it undergoes a meticulous refurbishment. The old analog receivers and transmitters would be replaced with a new quantum payload, a sophisticated system containing lasers capable of emitting single photons, super-sensitive single-photon detectors cooled to extremely low temperatures, and the complex optics needed to prepare and measure the quantum states of those photons. The existing antenna structure remains, but its purpose is completely transformed. It's no longer for broadcasting signals to millions. It's for whispering single photons between two precise points on the globe with absolute security. Once upgraded, these recycled quantum relays are deployed into a constellation, forming a secure backbone in the sky. They act as trusted intermediaries, receiving a quantum key from a ground station in one city, storing it securely, and then retransmitting it to another ground station on a different continent. Because the links between the satellite and the ground stations are relatively short in terms of atmospheric interference, the fragile quantum signals can travel the distance without being destroyed. This creates a seamless global web of secure communication that is immune to the computational power of any future supercomputer. The beauty of this approach is its powerful dual benefit. It directly addresses the orbital debris crisis by repurposing large, hazardous objects, and it simultaneously solves one of the most pressing challenges in digital security, creating an infrastructure that protects everything from personal privacy to national secrets. It's a profound demonstration that the solutions to our future challenges are often hidden in plain sight, waiting for us to look at our past investments with creativity and vision, paving the way for a world that is not only cleaner but also more secure and connected. But perhaps the most transformative power of this orbital recycling revolution lies not in the hands of governments or corporations, but in our own. Look up at the night sky from your backyard. Those faint, moving points of light aren't just stars or satellites. They're potential data points in the largest citizen science project ever conceived. This is the heart of community-based debris mapping platforms, a movement that turns every curious observer with a telescope into a vital guardian of our shared orbital commons. For decades, tracking the intricate dance of space debris was the exclusive domain of powerful military radars and a handful of specialized observatories, a closed loop of data guarded by technical and security barriers. But a profound shift is underway, driven by the realization that the sheer scale of the problem demands a network of observers just as vast. By opening this field to the world, we're not just gathering more data, we're fostering a global sense of ownership and responsibility for the space environment, building a grassroots army of orbital stewards one observation at a time. This model of public engagement has a brilliant and proven predecessor in the search for near-Earth objects. Initiatives like NASA's Asteroid Initiative and its accompanying Asteroid Grand Challenge have successfully mobilized amateur astronomers and backyard observers for years, creating a collaborative early warning system for celestial threats. Participants use their own equipment to scan the skies, uploading their findings to centralized databases where professional astronomers can verify and incorporate the data. The results have been staggering, with a significant percentage of new asteroid discoveries now credited to these dedicated citizen scientists. This powerful framework is now being adapted and expanded to tackle the challenge of human-made space junk. The core idea is identical: leverage the passion, time, and distributed geographical coverage of thousands of volunteers to create a monitoring web far denser and more responsive than any single agency could ever afford to build alone. The technology enabling this is as accessible as it is sophisticated. It starts with a simple telescope, even a moderately powered one available to many enthusiasts. What transforms this hardware into a debris tracking station is a suite of smart, user-friendly software tools. Apps and desktop programs now exist that can automatically identify known stars and satellites in a field of view, cross-referencing the user's location, time, and pointing direction with public orbital databases. When an observer spots an object moving in a way that doesn't match any known catalog entry, they can simply click a button. The software records a short video clip, logs the precise time and coordinates, and packages it all into a standardized data report. With another click, this anonymous packet of information is uploaded to a cloud-based platform where it joins thousands of others from around the globe. This is where the true magic happens. This flood of raw, crowdsourced data is ingested by powerful artificial intelligence systems. The AI's first job is correlation, sifting through the submissions to find multiple, independent observations of the same unknown object. By triangulating these data points, much like figuring out the location of a phone based on its signal strength to multiple cell towers, the algorithms can calculate a precise orbit for the new piece of debris. This new trajectory is then added to the public catalog, instantly improving the accuracy of collision predictions for everyone. The AI also performs a constant quality check, learning to recognize and filter out erroneous reports, like sightings of high-altitude aircraft or tricks of the light, ensuring the integrity of the overall dataset. This creates a beautiful, self-improving cycle. More observers lead to better data, which leads to more accurate catalogs, which in turn makes it easier for new observers to find and track debris, encouraging even more participation. The impact of this democratization extends far beyond the practical value of the data collected. It forges a powerful emotional and intellectual connection between individuals on the ground and the environment overhead. A person who has spent a cold night patiently tracking a fragment of a decades-old rocket body feels a personal stake in its fate. They become advocates for space sustainability in their communities, translating a complex, abstract issue into a tangible experience they can share. This global network of eyes creates a powerful, decentralized watchdog capability, able to monitor the skies over regions where official sensors may be sparse or non-existent, promoting transparency and shared responsibility for activities in space. It proves that the solution to a problem created by all of humanity can indeed be found in the collective effort of humanity itself, uniting professional and amateur in a common, critical cause. This incredible tapestry of individual contributions, woven together by technology and shared purpose, brings our journey through these 24 technologies to a deeply human close, setting the stage to consider how they all unite into a single, powerful force for change. Individually, each of these 24 technologies is a remarkable feat of ingenuity, a clever answer to a specific problem, but their true potential isn't realized in isolation. The real magic happens when we step back and see them not as separate solutions, but as interlocking pieces of a single grand system, a self-sustaining ecosystem in the sky. This is the blueprint for a true circular economy in orbit, where every output becomes an input, and what was once considered waste is the very fuel that drives progress. The connections are both elegant and powerful. Consider the beautiful synergy between the orbital 3D printers and the self-replicating robots. Those printers, fed by a constant stream of recycled metals harvested from defunct satellites, possess the ability to manufacture the components for new cleanup drones. But it doesn't stop at simple replacement parts. This process could be designed to create entirely new robots, effectively allowing the cleanup fleet to build its own reinforcements. The very material being collected becomes the means to collect even more, creating a positive feedback loop of exponentially growing capacity. The debris problem begins to solve itself, accelerated by its own mass. This virtuous cycle extends far beyond just cleaning up. The raw materials harvested by these autonomous systems don't just make more robots, they feed the entire orbital economy. The same aluminum and titanium being shredded and melted down could be diverted to construct the scaffolding for massive solar power satellites, turning yesterday's communications array into tomorrow's clean energy powerhouse. The water extracted from spent rocket fuels doesn't just support human life on a space station. It could be split into hydrogen and oxygen to fuel the very tugs and servicer craft that are doing the harvesting, creating a network of orbital gas stations that enables longer, more ambitious missions without a single launch from Earth. Even the data plays a crucial role. The advanced neural networks that track debris and optimize collection routes rely on a constant stream of information, a stream that is now enriched by the thousands of observations from community-based mapping platforms. This crowdsourced data makes the AI smarter, which in turn makes the cleanup robots more efficient, which provides more materials for the orbital factories, and so the cycle continues. This interconnectedness transforms our entire relationship with the space environment. We are no longer mere visitors who launch, use, and discard. We become stewards and managers of a dynamic industrial park. The hazardous cloud of space junk is reimagined as a distributed supply depot, a resource base that supports endeavors from scientific discovery to global security. The artistic installations crafted from historic debris are not an isolated cultural pursuit. They are a powerful symbol of this new ethos, created from materials provided by the same recycling infrastructure that supports the functional stations. They remind us that our future in space isn't just about survival and efficiency. It's about creating meaning and preserving our history. This holistic, systemic approach demonstrates that sustainability is never about a single silver bullet. It is about weaving a resilient web of solutions where each strand strengthens the others. The strength of this orbital ecosystem doesn't lie in any one technology, but in the countless synergies between them, proving that the whole is indeed far greater than the sum of its parts. And so our journey through the orbital junkyard comes to a close, not with a sigh of resignation, but with a sense of breathtaking possibility. We began by confronting a crisis, a chaotic cloud of 128 million pieces of debris, each a silent testament to our past carelessness. But through the lens of human ingenuity, we have witnessed a profound transformation. This isn't merely a story about cleaning up a mess. It is a blueprint for a new relationship with space itself, one built on the principles of a circular economy where nothing is wasted and everything has value. The very same materials that once threatened our satellites and missions are now being reimagined as the building blocks of our future, from the orbital 3D printers forging new structures from old satellites to the debris-powered propulsion systems that turn threat into fuel, and from the upcycled components giving new life to deep space probes to the cosmic art installations that transform pollution into cultural heritage. The true power of these 24 technologies lies not in their individual brilliance, but in their incredible synergy. They form an interconnected ecosystem where each solution amplifies the next. The metals harvested by autonomous robots feed the factories that build more robots. The water extracted from spent rocket stages fuels the very craft that perform the cleanup. The data crowdsourced by citizen scientists makes the artificial intelligence smarter, which in turn makes the entire operation more efficient. This is a self-reinforcing cycle of sustainability, a powerful demonstration that the problem of space junk actively contains the seeds of its own solution. We see that the discarded hull of a communication satellite can become the backbone of an orbital power station, beaming clean energy to Earth. We learn that a fragmented piece of a forgotten rocket can be compressed into a life-saving radiation shield for astronauts bound for Mars. We understand that even the smallest fleck of paint, guided into a controlled re-entry, can create a moment of awe-inspiring beauty for people across the globe. This is the overarching message of our time, a lesson that extends far beyond the vacuum of space. Humanity's ingenuity has the profound power to redefine waste as a resource. The crisis of orbital debris is not an endpoint. It is a catalyst, forcing upon us a new era of innovation that promises to benefit life both on Earth and in the heavens. It proves that with creativity and determination, we can pivot from a linear model of consumption and disposal to a circular one of renewal and rebirth. The challenges we face, whether in orbit or on our own planet, are not insurmountable obstacles but invitations to think differently, to collaborate, and to build a smarter, more resilient future. This future, however, is not predetermined. It awaits our collective will and participation, so we leave you with a call to action. Support the organizations and companies pioneering these space sustainability initiatives. Stay curious about the incredible technology emerging from this field. Follow the progress, share the stories, and marvel at the ingenuity. Most importantly, consider your own role in this story. Whether you are an engineer, an artist, an educator, or simply a dreamer who looks up at the night sky, you have a part to play in shaping a responsible and hopeful future in space. The next time you gaze upward, remember that you are not just looking at stars and satellites. You are looking at a frontier of both our past mistakes and our future potential. Remember that the junk of today may very well be the foundation of tomorrow's wonders. The page is turning, and the next chapter of our adventure in space is ours to write.